everyone. Thank you for coming to the first CPM seminar of the season. It is my pleasure to introduce to you Etienne Lantagne-Hurtubise. Etienne is originally a Quebecer. He did his undergrad, I think, at UDM. Then he went to Waterloo for the Perimeter Institute to do a master's. And then he started to follow me around. He went to UBC, but just maybe 20 years later. So we went to UBC and he did his PhD with Marcel France. So we're basically academic brothers, but he's my little brother. And then he kept following me and he took a postdoc at Caltech and he worked for the same people. So we're kind of very related in many ways. And then he landed back here, I think January 20 of this year. So even though you are a Quebecer, bienvenue, because we're glad to have you back in the neighborhood. And he's, I think, our latest RTM team member that just joined. So we're happy to have him in our community. And even though he's done everything very quickly, I think he just graduated from UBC in 2021, he still has a long list of publications and he managed to do a lot of stuff. He worked on graphene, twisted bilayer graphene, twisted bilayer superconductor, which was a very interesting idea, SYK model, other superconductors, quantum chaos, quantum-driven systems. So many, many different things. I'm sure whoever is going to meet him today and get the rest of the day is going to be very interested. So welcome to McGill. Thank you for coming to give our
Thanks for the very nice introductions. It's a pleasure to be here. I haven't visited in many years, so it's always good to be back. Right, so today I want to tell you a little bit about what I'm thinking a lot about these days, Rhombohedral graphene. I'll try to convince you why I think it's a very exciting platform for all sorts of interesting physics in two dimensions, both from theory perspective as well as from experimental perspective. Okay, so let's get started. Let me first acknowledge people that were really instrumental in getting me started thinking about these things. As you'll see as we go along the talk, this is very much an experimentally driven field, and theorists are playing catch up most of the times. And so I want to thank my experimental colleagues. We've done a lot of work with Stefan Lachberger's group at Caltech, transport and STM studies, and a lot of work as well more recently with Andrea Young's group at UCSB, transport and magnetometry squid experiments on Rhombohedral graphene center. And a bunch of students and postdocs that were really instrumental in pushing this forward. And then the theory side, I want to highlight a few people. So Jin-Min Ko was an undergrad working with me and Jason back in Caltech days, who did very beautiful Hartree-Fock simulations. Jiu Dong is a more fellow at Caltech at the moment, and he was also instrumental in developing some theories of superconductivity that I want to discuss. And then more recently, I've been working with Dan Levitan, who is also a McGill alumni, on collective modes. So I hope to have some time to discuss some of the latest ideas that we've been working on together. Okay, so and I want to flash a few new people. So this is a group at Sherbrooke, and there's a bunch of new faces, as well as a PhD student who will be co-supervised with Tabby and I, hopefully arriving at some point in the fall or winter of this year. Some visa issues. And before getting started with physics, I just want to advertise, that we have actually 3 open positions this year. So it's a really big year in terms of Sherbrooke department. So we have 2 positions in quantum materials theory or experiment, and 1 position in quantum information. So of course, if you're on the job market or have good candidates that are, please encourage them to apply. Of course, Sherbrooke being Francophone university, there's always the requirement that teaching be done in French. So it's helpful if people are either comfortable in French or are willing to learn in a reasonably fast time scale. Okay, so this is the advertisement slide. And now let's get talking about something. Okay, so in 2D graphene-based materials, in recent years, we've learned a lot about different platforms. There's, of course, the moiré or the twisted graphene systems. Everything that I'll be talking about today is untwisted, it's crystalline. It's the rhombohedral stacking that we see here on the slide. So let's imagine that I start stacking graphene layers together. Energetically, two layers want to have the A side of one layer sitting on top of the B side of the layer underneath. Energetically, this ensures that the remaining side is on top of an empty hexagon. Okay, that's energetically preferable. But now when you put the third layer in, you have various different ways of placing it. You can put it back on top of the first one. That's called ABA stacking. That's what graphite is. Or you can keep going in a staircase pattern. This is called ABC stacking. And if you look at it from the top, you have these three hexagons, the black, dark gray, and light gray. And it goes like ABC, ABC. So that's the Rhombohedral stacking. It keeps going in the staircase section. These two stackings are very different. And ABC has attracted lots of attention because of its interesting electronic structure. So if you look at close to charge neutrality, this is the black line here. For bilayers, it's roughly a quadratic band touching. For trilayers, it's a cubic band touching, plus corrections and so on as you add number of layers. But if you apply now an electric displacement field perpendicular to the sample, it opens this gap, this band touching gap. So it opens a gap in the band touching structure, and it gives rise to these, let's say, purple or orange bands. The particular feature of note here is that this band bottom, the valence or conduction band edges are very, very flat, as reflected in the density of states in the right panel. You have a divergent density of states that's reflected on the whole singularity of the band structure, and that is dramatically amplified with the displacement field. You see by comparing the black lines. Okay. So in a way, it's a system where you can tune the effect of correlations through dramatic change in the density of states. Okay. So you can tune by putting this in the dual gated setup. You can control both the displacement field and the chemical potential. You can tune the doping level through this band structure, and you can also tune the correlations. It's very tunable platform to study correlated outcomes. And it's also extremely clean because of the lack of twist angle. You can encapsulate it in form of nitride, and so it's a very clean system. It has very long maintenance. That's very few periods. Right. So now what happens if you crank up the effect of interactions through flattening the bands? You're going to see some symmetry breaking or polarization physics. So if I just look at one of these systems and I start doping it either with electrons or holes, the symmetric state, the band structure expectation goes like this. You have 4 flavors because graphene, remember, has 2 values at low energy, plus the 2 spin components. So you have 4 flavors, and the band structure expectation is that you're just going to fill electrons or holes equally within these 4 flavors. However, if exchange interactions get important, then you will drive polarization. So the system will want to polarize to reduce the effect of exchange interactions. This is very similar to sonar ferromagnets and metals that you may be familiar with, where spontaneously you may decide to put more electrons in one spin component. This costs some kinetic energy, but you gain exchange energy. So it's a balance between the two, and there's a Stoner criterion which tells you when interactions are strong enough beyond some threshold, you're unstable to this. Okay. Now, the difference with graphene is that you don't have only spin, you have also valence. So the landscape of symmetry breaking is much richer. You have many options. So for example, you can valley polarize by putting electrons predominantly in one of the valleys. You can spin polarize, which is the analog in the usual Stoner ferromagnet. You can have other combinations, like you can have spin and valley locking, like this. You can just choose 1 out of 4. So be both spin and valley polarized at the same time here. You can also change the basis if you want. So if you're not happy with the spin and valley flavors to choose from, you can hybridize valleys together. This is called inter-valley coherent state, where you form a new flavor that is a combination of the 2 valleys that alternate. So here blue and red would be with electrons predominantly in one valley or the other, and that alternates as you go along the place. Okay? Because you're hybridizing valleys, this is breaking translation. It's a charge density website. Okay, so there's many options, and part of the interest of the field is trying to figure out which one is favored under which conditions, and try to understand. Okay, so how do we know this? So there's many experiments that you can do. Maybe the simplest to pick up these phase transitions when you polarize between some of these different options is compressibility. Oh, this is inverse compressibility, but wait. If you change on the x-axis the electronic density, either electronic or hole-like, and you change the displacement field on the y-axis, you can look at the two-dimensional phase diagram where the red or yellowish colors are metals, and they're separated by these negative compressibility feature that constitutes first-order phase transition. So you go from here to here, you're going between two different metals. There's a first-order transition in between where you're changing the symmetry. Okay? And with quantum oscillations, you can figure out the degeneracy of Fermi surfaces and the like, so you can try to piece together what the phase diagram is. So that's been observed in both bilayer and trilayer, now up to 10 or so layers. Graphene, the physics is always a little bit different, but that's the universal features. You get these different symmetry values at finite densities. Okay, and I think the reason why many people got very excited about this platform is the observation of superconductivity about 4 years ago. These are two experiments from Andre Young's group in bilayers and trilayers. They look relatively similar. You get some very low TC superconducting phases, but they appear in the phase diagram close to these symmetry breaking transitions. So for example, here you're changing the symmetry, very close to that transition, you get a sliver of superconductor with very low TC. Same thing here, and some of these phases are spin triplet. They have gigantic Pauli limit violations, so the superconductivity survives very large magnetic fields in the plane, which way beyond what a spin singlet BCS superconductivity survives. There's other evidence that strongly suggests, let's say, that there's spin triplet, at least this SC2 and this one. This is kind of unconventional superconductivity. Now the story keeps getting weirder. So last year, there was this experiment, which was published eventually this year, from Lange's group at MIT. They looked at systems with a few more layers, tetralayers and pentalayers. And here in a particular region, of the density and displacement field phase diagram, you get these 3 different superconducting pockets. But if you go at temperatures slightly above superconductivity, what you find is a very weird normal state. These are quantum oscillations here. I don't know if you can see, but there's a single in this region, which gives rise to this roughly this SC1 pocket. There's a very clear single frequency oscillation, which corresponds to a single Fermi surface. And if you know the total density, you know the frequency of oscillation, you can check that there are no more electrons in this region. They're all in the same flavor. And this should be completely inevitable to pairing, right? It's a single spin and single value. So what is going on? Right? It's not only this would be an orbital and a spin ferromagnet. There's no time reversal, there's no inversion, there's no mirror, there's no symmetries that protect the usual BCS. This is a very weird thing. If that's true, then it's a single flavor superconductivity. So it must be spin triplet because there's only a single spin there to begin with, and it's also a parity. It's probably chiral. And the evidence is this. So there's some hysteretic switching here. So of course, if I go back here and I just look at the normal state above DC, this has a spin magnetic moment and a large orbital magnetic moment because there's a strong Berry curvature that's uncompensated in the signal netting of graphene. Okay, but that couples to a magnetic field. And indeed, you can pick which flavor you select out of the 4 by hysteresis loop. Right? You put a magnetic field in, let's say, up direction, it will pick some combination, and down direction will pick an opposite combination. You can switch between the two. Since it's first order, you have this hysteretic switching. So here it's at high temperatures above the superconductor. This is out of plane magnetic field. This is RXY. You see this hysteretic switching between the two solutions. Okay. Then you decrease temperature, then this disappears. And then at low temperatures, there's something very weird reappears. You're switching between two superconductors. If you look at RXX, it's also 0. So you're training your field this way. It's superconducting. There's a transition and it's superconducting again. And then there's the hysteretic loop the other way. Okay.
So in terms of temperature, you're below the TC?
Yeah, TC is about 150 to 200 here. Yeah. So here is below, way below TC. Here is above.
And the quantum oscillations are above TC.
The quantum oscillations are above TC. Yeah. So this is very weird. I'm not aware of any other system that does this hysteretic switching as a function of magnetic field between two superconductors. The picture that they propose is something like this. So let's say I have pairing arising from the K valley for some magnetic field direction, let's say up. As I'm switching back, eventually, this state becomes metastable. Eventually, it will want to transition to the blue solution. But in between, you'll have presumably some domain structure. And that introduces some resistance because you can't scatter with Cooper pairs with center of mass momentum k to k prime. You need to give some momentum to scatter across this domain wall, presumably gives rise to some resistance that explains the speed. And then on the other side, eventually you're on the okay. This is controlled by out of loop. It's extremely weird state. So yeah, the ground state can be selected by out of plane magnetic field. It's single value pairing if we believe the story. So Cooper pairs also carry by default non-zero momentum. So this is here this way. And yeah, it cannot exist in the weak coupling limit. There's no symmetry that guarantees that you're going to have a partner at -k to pair with on the Fermi surface. Okay, there's no nesting at all. So it has to be kind of intrinsically strong pairing if that's the right picture for the superconductor. There's a bunch of theory work. It's extremely weird superconducting state. Yeah, and then there's some more exotic stuff. If you keep going along the series, there's experiments at 6, 7, 8, 9 layers. And there's some really wild claims, actually. If you read these papers, there's some claims about superconductivity from anions and the quantum Hall effect. All sorts of weird things. I'm not really prepared to defend those statements, but this is what you find in some of the recent literature. But for sure, there's very interesting interplay with charge density wave, nematicity, some quantum Hall physics that appears as a function of magnetic field, which is very close in the phase diagram with some new superconductors. What is going on there? I don't really know. Yeah, but a bunch of interesting experiments. This is more like an advertisement for some of the interesting activities. Okay. Today, I want to backtrack and tell you two stories. Try to carefully look at what may be happening in those systems. The first story is coming back to these 2 and 3 layer systems, and I will try to tell you what I think we learned from inducing spin-orbit coupling by hand, if you want, in the graphene system. What that can hopefully tell us about the superconductivity there. And then the second story is of this tetra and penta layers. If we accept, let's say, that superconductivity arises from these valley and spin polarized states, there's some actually very unique features that you may be able to see by looking at these collective modes of these single values. So, yeah, any questions before I start? Okay, good. So let me come back now to the spin-orbit coupling story. And then we've been working on this for many years, and of course, many other groups have also contributed to this. So this is some of the references that yeah, we can look into for details. But basically, the idea is this. So we already have a rich phase diagram in these graphene systems. And one of the ways that you can quantify and try to get some different phases is by inducing spin-orbit coupling. And the way people can do this is by stacking your 2D graphene sample on top of a monolayer TMD like WSC2 or WSC2, which has very strong spin-orbit coupling, and by proximity effect, you're going to inherit some of that. And when you do this, you get qualitatively different phase diagrams. So this is the transport results. So this is resistivity as a function, again, of displacement field and hole doping, in this case, for bilayer graphene with WSC2 substrate. You find a large region of superconductivity that is very interestingly very asymmetric in displacement. So there's a large superconducting region, and it only appears on one side of the displacement field. And this reflects the asymmetry of the stack. So WSC2 is only on one side of the device. And for a particular side of the displacement field, these, for example, here we're hole doped, so the valence band wave functions are pushed closer to WSC2 for one side of the displacement field. And for the other side of the displacement field, they're pushed away from the proximity effect is much weaker in this case. And that corresponds to the region where superconductivity is not seen, and superconductivity is stabilized for this configuration. If you go to electron dope, it's reversed. It's different charge carriers. And this idea is not new to this experiment. It was proposed many years ago in the spintronics community. People were interested in this effect as a way to turn on or off the spin-orbit splitting in some, this is called this a spin-orbit valve. And there's other groups that have picked up on this and confirmed that it expanded this original experiment. And one of the things that we got excited about is TC is vastly enhanced. So remember, in bi-layer graphene specifically, TC was about 25 millikelvin without the tungsten dicellulite or the dicellulite substrate. So the TC is very strongly enhanced to about half a Kelvin in these spin orbit proximities. Okay. So this is an experiment that I was not personally involved in, but it's very beautiful. Stefan's group followed up on this by constructing 6 different flakes of binary graphene. They're all deposited on the same WSC2 substrate. And now what they can do is change the relative twist angle between the graphene and tungsten dicellulite. And the reason to want to do this is that this modulates the spin orbit coupling. This was predicted with ab initio calculations some years before that. And there's a symmetry-based reason for this, which is that you have 2 hexagonal lattices, and they're different. They have different lattice constants. But if you think about why PMD has a large spin orbit coupling and not graphene, it's because this mirror symmetry is strongly broken in those. And how much of that gets translated to the underlying graphene depends on the relative orientation. So you can take that here, it's very large, because if I pick a sublattice of graphene, it's sitting underneath, let's say, tungsten, and the other is sitting underneath selenium. It's very strong symmetry breaking, whereas at 30 degrees, each sublattice of graphene sits halfway between the 2 atoms. So in a leading order, the effect of spin orbit coupling should vanish here. And this was confirmed in ab initio simulations. So the idea is by tuning this relative orientation, you can tune the amount of spin orbit coupling that you induce in your graphene. But you don't need to rely on numerical simulations to try to guess. You can independently contact each of the 6 planes for transport measurement, which is what the PhD student Lantagne did. And there's a way to extract the spin splitting in Lantagne levels if you do quantum Hall measurement. So you can independently extract the induced spin orbit coupling for each of the flakes in the transport independently. It's a very beautiful fabrication challenge. And this is kind of the summary of what you get if you do this. So you have 6 flakes. They have spin orbit coupling ranging from half an MeV roughly to 1.6. And here you can look at the optimal TC as a function of the displacement field that you apply. And there's a kind of non-monotonic trend going on where if you increase spin orbit coupling, the first thing you notice is that the phase space of superconductivity is reduced. So you need to apply stronger displacement field to see the superconductivity. If you go from blue to yellow, however, TC is strongly enhanced from 150 millikelvin to 500 in the largest spin orbit. So yeah, there's this kind of opposing trends. First, the superconductivity is pushed to higher displacement field, but the critical temperature is not high. Okay, and this is very non-trivial constraints for theory to understand where that comes from. And yeah, what we started thinking about back then is trying to understand the normal state. So superconductivity is, of course, much harder, but can we understand even what's the normal state from which this arises? And this is where, maybe can inform pairing mechanics. Okay, so what's the normal state? This is work that our undergraduate student back then did by performing self-consistent Hartree-Fock in binary graphene with spin orbit coupling. Just to remind you, if you're familiar with Hartree-Fock, the idea is that you have some time-bending description with some spin orbit coupling. That's in this case that's induced by proximity effect, and then we're splitting the Coulomb interactions using some consistent mean field ansatz. So we define an order parameter for the mean field, and alpha and alpha prime here are spin and valley flavors. So the idea is to capture all possible types of symmetry breaking in spin and valley sector. If you pick an ansatz for an order parameter, you can decompose the interacting part of the Hamiltonian and then figure out numerically what's the best Slater determinant. With that Slater determinant, you can update this mean field over parameter. So that's called covariance matrix, and plug it back in until you right? And because the problem, the landscape is very complicated, we find it helpful to do this loop separately in each symmetry sector of the problem, then compare the final energies. And I spare you all of the details because there's a lot of different phases that you find as a function again of density and displacement field. But if you compare with the experiment, and in particular, I want to look at what's happening to the superconductor, dark blue. As I said before, as you increase spin-orbit coupling from left to right, it's getting pushed away to higher displacement. And the normal state that has the same behavior in Hartree-Fock is this orange phase. It's getting pushed away to higher displacement field and densities as you increase spin. Okay? It's getting replaced by the pink phase. And so what is this? The spin phase is a spin value locked state where I pick 2 flavors out of 4, but I pick these ones. And this happens to be the one that spin-orbit coupling prefers. Tungsten diselenide has this particular type of spin-orbit coupling, Ising spin-orbit coupling, and it does that. Picks out of plane spins that are opposite to valleys. So that's just a kind of trivial choice. If you have strong spin-orbit coupling, you're going to want to do that. And the orange phase is symmetry broken. What it does is it counts the spin. So I start with a spin value lock state, which is purely out of plane, and I count the spins in the. Okay, so it's a ferromagnetic instability where I nucleate an in-plane moment. Okay, on the Bloch sphere, it looks like this. So let's say blue is value k prime, red is value k. Instead of being opposite on the Bloch sphere, they now have a finite in-plane moment. This is what we find in Hartree-Fock. And if I want to distill a little bit this generics and try to understand more analytically how this may come about. So this is driven by competition between 2 terms. So in graphene, now let me call this NK. It's the order parameter for the transition. It's the spin polarization in value k. Okay, so it's basically the magnitude is what's the polarization density, and the direction of this arrow is where's the spin pointing at each time. So if I want to write a Ginsburg-Landau free energy from this, then I have a first term, which is kind of Coulomb interactions and kinetic energy. It's isotropic, so it just wants to polarize. When this coefficient becomes negative, it just wants to polarize in whatever direction. This is the leading order term. And then you can check it. It's not a trivial statement, but you can check it. In fact, this term has too much symmetry. You can rotate these order parameters independently in the 2 values, which is that's too much symmetry for graphene. There's only a S global SU2 symmetry. So you need a term that fixes the relative orientation. And that's this term. We'll sometimes call it the Hund's coupling because it likes to, it will set the relative orientation of the spins to 2 values. And it turns out to be ferromagnetic in this particular system. There's no theory and experimental evidence for that. So what this does is it wants to align the spins of the 2 values together. This is what promotes ferromagnetism. And then there's spin-orbit coupling, which wants to do the opposite. They want to anti-align the spins in values k and k flat. It's the z component of the spin wants to anti-align. So if you're trying to, there's a competition between these 2 things. This wants to anti-align but out of plane. This wants to align but doesn't care in which direction. Turns out the best compromise is not to try to polarize out of plane. You want to polarize in plane. Okay? And so this is the best compromise you can find. And as a function of this parameter here, this lambda over some J of energy units, you get a spin value locked phase when the spin-orbit coupling dominates, and then for lower enough spin-orbit coupling, there's a second order phase transition where the in-plane magnetization here starts ramping up. Okay? So the transition from this configuration to this configuration, where spin-orbit coexists with in-plane magnetism. Any questions on that part? Okay, so that's the modeling. And one interesting thing to note is that this can take, so it's a symmetry breaking transition. What does it break? It breaks spin rotations, but with spin-orbit coupling, the system has only in-plane spin rotations remaining. So it breaks these U1 spin rotations by picking a particular in-plane direction. So that's the symmetry that it breaks, and it's a continuous symmetry, so you should get some low energy connected modes. There's some Magnon modes, particular types of spin waves. And this then motivated us to look at possible pairing mechanism from these connected modes. This is kind of some variant of a spin fluctuation mediated superconductivity. Right? You can imagine that you have these magnons in the system, and we can exchange, electrons can exchange these magnons together and potentially give rise to.
Yeah, so what's this microscopic origin of this Hund's coupling?
Yeah, it's lattice scale Coulomb. Yeah. If you look at the long range part of Coulomb, it has these independent rotations in the 2 values, it's SU2 times SU2. You can think about it this way: long range part of Coulomb is small momentum. and the valleys are separated by a large momentum. So if you're only allowed small momentum scattering, you can only stay within the same valley. So that gives rise to this guy. But if you're at lattice scale repulsion, it allows you to transfer large momentum between them. But yeah, so lattice scale repulsion gives you ferromagnetic noise coupling. What's not clear is that, of course, there's not only Coulomb, there's also phonons and impurities and so on. In some systems, people argue that if electron phonon coupling is strong enough, it can actually change the sign of this thing. So you should check experimentally whether you see a ferromagnet or not. And at least they do see a ferromagnet. And we're quite confident that this is the right sign. Okay, so then you can ask what are these collective modes, and so there's a theory paper about this. This is Zhu Dong and Jason. Yeah, it turns out that it's a complicated problem because if you don't have spin-orbit coupling, this is just a regular ferromagnet, an SU2 ferromagnet. It has a quadratically dispersing Goldstone mode in the ferromagnetic phase. But then if you add spin-orbit coupling, the symmetry changes. It's U1 ferromagnet or XY mode if you want, and that has linearly dispersing Goldstone mode. And then because we have a critical point, eventually as you increase spin-orbit coupling, and we're going to lose this counted phase. So that there's a second order phase transition, there has to be another mode that goes critical. So this is the dashed line here, goes critical in the transition. And then on the Bloch field, these two modes are doing this. So the Goldstone mode is these azimuthal fluctuations. So it just, you pick the direction for the order parameter, and then that rotates it like a usual Goldstone mode. And the critical mode is the one that does this. It's in orange dash line. It's the critical mode for the character. So you have two low energy magnons. Yeah, it's the C2 limit, it's U1 limit, and at a critical point, you have these two gapless ones, and they can mediate pairing. Okay, I want to say that we didn't do some serious numerics on this, but parametrically, this gap here to this critical mode, even when you're far away from the transition, should be relatively small in units of the Fermi energy. It depends on the ratio of the Hund's coupling to the isotropic part, the long-range Coulomb part, but that should be quite small. So it's probably quite low line. So no serious numeric. Okay. And then if you think about what can this mediate superconductivity? Well, yes, it can, but it will be a little bit different than usual BCS because it's a magnon. So if you take two electrons that want to form a Cooper pair and they exchange a magnon, then it will flip their spins. So you need to go to the other band. You really need to be in this limit where you have both majority and minority spins, like this, and exchanging magnons can flip you between bands. The crucial part of the story, as relates to spin-orbit coupling, is that you get this prefactor that's goes as cosine squared of theta, or theta at this angle. So if you lose scanting, like you're at the critical point where this goes to zero, this is actually maximum. There's a symmetry reason where this prefactor is maximized at the transition, but it actually vanishes by symmetry. If you remove spin-orbit coupling completely, you get this, as you do for a magnet. There's a conservation law that forces this pairing mechanism to vanish. The idea is that spin-orbit coupling would enable pairing through these exchange of magnons by reducing the symmetry of the originals.
Sorry, I'm a bit confused about the arrows you have there.
Yeah.
So the pair, is that the pairing direction, or what is it?
This is the scattering of Cooper pairs. So this electron and this electron are like one putative Cooper pair, and they exchange a magnon and they go to this other. Yeah. It's kind of this electron flips to this one, it hits a magnon, and it gets absorbed here.
Okay.
Yeah, so it's like two electrons exchange a magnon. Yeah, it's a single magnon exchange. And I'm happy to chat more afterwards if you're interested why. And there's a symmetry reason why this process actually gives you zero pairing if you have full SU2 symmetry. You need this spin-orbit coupling to enable this, and that's why you get this prefactor. So that's the story, and yeah, there's also Chubukov, and Chubukov has some follow-up, a slightly different setup, but similar ideas as well. Okay, so that's the story, and yeah, this is the main driver of this idea. Yeah, so we have no idea whether this is actually true, but what we're trying to do is again go back first to the normal state. These are experiments that we collaborated on with Andrea. This is now ABC trilayer graphene with tungsten diselenide. And the idea was to check whether the spin camping physics happens in the normal system. If that's true, then what is the signature of this transition? It should have an in-plane magnetic moment, but no out-of-plane moment, but the out-of-plane part exactly comes. And so that would be resolved with a squid on tip. Since you put a little squid loop on a tip, and then you're very sensitive to magnetic fringe magnetic field that emanate from a magnetic sample. So if you first look at the transport and transport here and compressibility here, and you already see something interesting. So remember that the polarization of the wave function as a function of is such that on one side you're going to have strong spin orbit coupling and you're close to the substrate. The other side you will get weak spin orbit coupling because you're far away, and that changes between electrons and holes. So these are the quadrants we expect, strong and weak spin. For the strong spin orbit coupling case, here you get a superconducting phase that was not present before. And there's a tiny one here in the other quadrants. We're going to focus on this larger one. Then you can ask the question, what is the normal state here? This new superconductor that is seemingly enabled by spin. This is, now you can do squid on tip. And there's a very clever way that you can separate the signal acquired with different biasing magnetic fields to be sensitive to either the in-plane magnetization of the sample or the out-of-plane. With this paper, it's a very clever experimental technique, and it allows you to separate the signals. So in blue, it's the in-plane component of the in-plane magnetism, the sample, and in red, it's the out. So let me start by the quarter metal. Remember that quarter metal, sorry, I should have explained this, sorry, this nomenclature in this business. Full metal is when you have all the flavors, so it's symmetric, all spin and magnetic flavors. Half metal means you have half the flavors, so it's polarized in two spins, okay? And quarter metal, you put 1 quarter. You have 1 quarter. Well, quarter metal is a spin and value polarized single flavor system, and that has a large Fermi curvature, so large out of plane moment. And this is reflected in the data as well. You see that this quarter metal region is very strongly out of plane magnetized, as you would expect from an orbital for a magnet, but it has nothing in the in-plane part. Okay? Of course, electrons can only it's a 2D system, so they can only have orbital moment like this pointing out. So this works out. If you look at the half metal phase, which is now relevant for the superconducting phase, if you go to the strong spin orbit coupling case, you see no signal in the out of plane direction, but a large signal in. So this is exactly consistent with this idea that you get in plane for a magnet with compensated moments in the out of plane direction. If you go, however, to the weak spin orbit coupling side, you see the signals are more comparable. So it looks like the spin orbit coupling is much weaker, and so here you get signal. Basically, the system wants to polarize whichever way the field points. There's no strong end result in the magnet. So this really confirms that this half metal phase is spin captured. You can try to compare by looking at here is the in-plane magnetic moment. And you try to compare it to transport measurement, and you find the blue region is where the superconducting is. And if you try to compare, it looks to be almost exactly ending where the camping disappears. So this new superconducting phase arises near the onset of the spin camping order. It's of course not quite clear whether that's the two phases are competing or if the collective modes of the camping phase really help superconducting. But there's also independent evidence that this superconducting state has an in-plane moment. If you take a transport cut along this dashed line, you might see, you find that the extent of the superconductor in light blue is extending with magnetic fields. It's weird behavior. You apply an in-plane field and the superconductor is growing. So it either has an in-plane moment, the superconductor itself, or it's very susceptible to getting it. It's very polarized. So, of course, we can reproduce this onset of camping in Hartree Fock as well, roughly with the right phenomenology and the right displacement field. But yeah, I think the main question is, whether this coexistence of these two effects, is it a coincidence? Is it competing, or is it a clue from the Fermi mechanism? we don't really know. And the question is, how does this scale the number of layers? How one could measure these collective modes? How much time do I have?
15 minutes.
Okay. Yeah. Are there any questions on this before I switch to?
So
Yeah.
is this features unique to this trial, or you can see it is unique by layers?
Which features?
This can be.
Yeah, so we don't know. The nano squid was only done in dry layers for. Yeah,
But here it is speaking at this.
yeah. We did that for bilayers. This is everywhere. Yeah. So yeah, but we don't know. I hope that someone will do the experiment to check. And of course, for bilayers, we also had this experiment that changes the spin orbit coupling in situ. Of course, this physics also is very sensitive to the spin orbit coupling. That's what's driving the Canted phase. So there should be it would be very interesting to systematically look how this changes from.
Is it easy to calculate this effective spin orbit coupling in place of this WSE2?
You would have to do it with epinitial, right? It's how much spin orbit coupling you inherit by hopping to the WC2 band and that. People have tried to do that, but I think you don't actually need to do it because experimentally you can measure how much of it is in the graphene. That's very nice.
And does it increase the number of layers or
in graphene? I'm not quite sure. I guess not strongly because the physics is very strongly polarized to the top layer or the bottom layer anyways. I guess it doesn't strongly depend on the number of layers. What we need to check. Yeah. Okay, but hopefully this is an example of combining different experimental techniques in 2D with very clean and reproducible samples allows you to constrain a lot. What can potentially be the origin of right. So I will leave these open questions here and then kind of move on to a slightly different story. So the system of Rhombohedral, but now we're looking at these 4 and 5 layer systems where it is believed that the moment that the superconductor arises from the single spin and flavor, single spin and dipolarized solution. So that would be this triangular shape. So one thing that's an important feature of these systems as well is that the Fermi surfaces are not circular. So yeah, the dashed line is some circle, and because the system has C3 symmetry, really, there's no reason that the Fermi surface should be a circle. It's actually a triangular shape like this. This is what we also call trigonal arcing. It's a cubic and momentum term that makes the Fermi surface triangular. And this is quite important for superconductivity because if the Fermi surface was circular, then you could have BCS instability by just carrying electrons with opposite momentum. The fact that it's trigonally warped means that you no longer have this weak coupling. But what we argue in this work is that the same feature, this trigonal warping, makes collective modes that are usually dark and linear optical response, they make them visible. It's the same symmetry breaking. And so if you were to measure optical conductivity with a microwave regime, you could find some sharp features associated with this. That's what we talked about in this paper. Ben is an expert on superconducting collective modes, and yeah, when we started working together, when I read the short book, we started looking at this these new exciting super. So Ben told me about clapping modes. So I don't know if you know about this story. It's about maybe I should backtrack and say that when we talk about superconducting collective modes, usually we think about the Higgs mode with the amplitude fluctuation of the order parameter. There's been lots of interest in that. This is a slightly different thing. If I have a more complicated order parameter, like for example, a chiral superconductor. So it's a px plus ipy. It's a 2-component order parameter. And the fact that it's more complicated, it has 2 components, gives rise to more options for collective modes. Okay. And so here's how a clapping mode works. So I have a chiral superconductor. Let me assume it condenses as px plus ipy. So what that means is that if I look at the phase of the order parameter along the Fermi surface, I will have some winding of one winding, 2 pi winding down the origin. Okay. And of course, the px minus ipy would be the opposite winding. And both options are in principle possible if your system has standard. And let's say I pick spontaneously one of those, the plus combination, the fact that there is a time reverse channel that is uncondensed, but FTC was an equally valid solution, it actually has a low energy consequences, which manifests as orthographic fluctuations. This is what's called generalized clapping modes, in analogy to some old superfluid helium-3 work, where this similar physics happens. Okay. And the way this looks is that, okay, I have a condensed channel that I picked, I call it delta plus. This has a mean field value now. And then there's a fluctuating phase mode and a fluctuating amplitude mode. So far, it's the standard story. Right? And in the uncondensed channel, or the time reverse channel, however, I don't have a mean field value, it's 0, but I can have fluctuating fields. And this is the parameterization that we like to use, so that I have this, I factor out the same phase mode in front, and then I have these two real fields, A and B, that can be there. And now it's maybe not so clear, but if you go back to the PXPY basis and you see what is this fluctuation mode A and B do, the A mode increases the PX orbital while the PY orbital is decreased, or vice versa. So it's kind of a breathing mode, if you want, of the order parameter. The blue and yellow are real and imaginary part of the order parameter, and the dashed line is the mode. And the B mode, instead of breathing in and out of phase, it changes the relative phase between Px and Py, so it actually brings them closer together and farther away. Apparently, that's the origin of the clapping mode, because the mode does like this in the complex plane. Okay, so there are two connected modes again. Okay. And observing them would be very interesting from a fundamental point of view, but also are interesting because they reveal the presence of uncondensed channel. So in constrained Hering symmetries, and they can be in gaps, so not damped under the right circumstances, or something like this. So in the ideal case, you get, for example, through the peak at 0 frequency in the real part of conductivity, and there's some quasi-particle contribution for frequencies above 2 times the mean field gap. And inside the gap, you can have some sharp resonances that are called clapping modes. Yeah, we'll explain the meaning shortly. However, the usual story is that this is not visible in the linear optical response. The traditional BCS superconductor, none of this is visible, none of this couples to electromagnetism to first order. Systems with inversion symmetry, actually, inversion symmetry precludes linear coupling to right? This is why it's so hard to see Higgs modes, for example. Okay, so how is this story different? So, first, let me tell you what people have been thinking about in the literature, how to allow this optical coupling. The most successful way to do it, and there's been some experiments on this sense, is to break inversion symmetry exclusively by applying a DC supercurrent. Okay, so and that's been done both for conductive modes and also for regular quasi-particle contribution to conductivity in superconductors. And the kind of basic idea can be summarized like this: I have a, let's say, usual BCS superconductor like this with a gap, and inversion symmetry of the system precludes optical couplings. But if I apply a supercurrent and this shift of and distortion of the band structure, it's also called Doppler shift of the band structure, and this allows now optical coupling, a resonant optical transition between the OLAC and electroLAC. Yeah, the underlying reason being that it breaks inversion symmetry. But we can do the calculation more seriously. Yeah. This is what it allows you to do. Now, the insight from Ben is that in these superconductors that are trigonally warped, it kind of does the same thing for free. If you again compare the circular Fermi surface, which is kind of inversion symmetry and similar to this situation, versus a trigonally warped Fermi surface, which pushes the energies up in this direction and down in this direction. It does kind of a Doppler shift, except it's modulated around the Fermi surface. But nevertheless, the fact that this Fermi surface is trigonally warped allows linear coupling to electromagnetism, which is controlled by this trigonal warping parameter. Okay, this is the result, and it of course breaks inversion symmetry as well around this Fermi surface. Maybe I don't have too much time, and this is getting a little bit technical, but this is a kind of symmetry-informed Thor model calculation where we have a single spin in valley, so they're flavorless fermions with the trigonal warming Fermi surface shown here. And then we have pairing interactions that we assume comprise two channels that are competing with each other. These could be generic channels with generic angular momentum, but let's say if it's a competition between P plus IP and P minus IP, these form factors here would just be winding in a positive or negative direction along the center. Yeah. And then this is all path integral based, but details are in the paper. But just to recap the strategy, first thing is that you decompose these interactions here in the Cooper channel using Hubbard-Stratonovich, and then you find a saddle point which determines what the Kappa function. Okay. And we assume that the Carroll solution is preferred, so you'll pick either one or the other of these solutions. Then you can expand around the saddle point. This will give you the fluctuations of the conductive modes, such as the kinetic mode. And then you couple the theory to electromagnetism, and then what you need to do, instead of doing like a brute force Kugel formula, what you can do, which is equivalent, is you couple to electromagnetism, and then you integrate out the fermions and the conductive modes, and this renormalizes the electromagnetic action. Right? And from that, you can read out the coefficients that you want, which is electromagnetic tensor conductivity. And when you do that, you get, because the model is so simple, you get some analytical expressions that are perhaps not so useful, but what we can extract out of it is that there's a sharp feature that appears at the frequency, which is given by this expression. It's square root of 2 delta if the modes compete exactly. So this delta G here is the difference in strength between the two channels, G1 and G1 minus G2. Sorry, going the wrong way. Okay, so the competition between these two channels, if the system is time reversal symmetric to begin with, then these are equal. Right? The system just spontaneously chooses, in which case this thing is 0, and you just get a mode of square root 2 delta, which is the usual story for classic modes. Of course, in reality, time reversal symmetry is broken because we've already picked a normal state with a particular value of the orbital moment. So, well, if this is not 0, what it does is it pushes the electric mode frequency up. If it doesn't push it beyond the gap, then it's kind of positive. So, okay. And yeah, this is some quasi-particle notification. Okay, and the magnitude of the signal goes as eta squared, where eta is this trigonal warping. If you put this another way, if you're familiar with these calculations, if you think about it from a Kugel formula, it's a commutator between two current operators. Each current operator is proportional to the trigonal. So you can create this. Okay. So yeah, this is a summary slide. So the take-home message is that this trigonal warping in a single valley superconductor, it enables linear optical response and therefore access to potentially some of the interesting connective modes, sub-gap connective modes in Carroll superconductors. This may be relevant for these Rhombohedral systems. And this would be microwaves in terms of energy scale. It's quite low PC superconductor. And so thinking about ways to measure this response using architectures inspired by circuit QED. I forgot to say that this is sigma XX, but really, if you're interested in polar current, for example, the sigma XY shows the same sharp feature at the same frequency. In the sigma XY, frequency dependent sigma XY. And yeah, because these are microwaves, then the relevant kind of optical, it's not really optical, it should be microwave photon experiments, and the community that has developed a lot of tools to do microwave spectroscopy is circuit QED. We use resonators and cavities to couple to materials, and there's already been some pioneering work by various experimental groups where you couple some interesting, let's say, superconductor interest in a microwave resonator, and you're able to backtrack. Usually the superfluid stiffness that is measured rather than the conductivity, but similar ideas. We're also thinking about the ways to utilize these circuit QED architectures, some of this low energy response. Okay, so that's all. Let me just say, I hope I convince you that this is very interesting systems. It has correlations, you get induced spin-orbit coupling and superconductivity, very same, very exotic forms of superconductivity that are still poorly understood, and it's very diffuse. Okay. There's very exciting physics. So it's only been 4 years, and it's very hard to wrap our heads around how fast experiments have been in seeing a bunch of very unconventional states of matter, often found in the same device. And yeah, I think we're getting a handle on what the normal state phase diagram is, what are the symmetry broken phases, but superconductivity is sort of the enduring mystery of that. The role of conductive modes may or may not be important, but in order to figure this out, we need new experimental tools that are frequency resolved. Yeah, so this is mine. Thank you.
Thank you.
Okay.
What's the energy scale of the collective bolts in the Rhombohedral state? Like
Yeah. So it's hard to know for sure because we didn't do honest numerics. It will be a small fraction of Fermi energy. So probably sub-MeV, I would guess.
But also microwave stuff, yes.
No, probably higher than that. So the superconducting gap is much lower than that. It's microeVs, tens of microeVs. So maybe it's terahertz or the magnon modes. Or terahertz of magnon. Yes.
Yeah, I was wondering, so when you have these bilayer or trilayer graphene on the tungsten I guess so you can tune the spin orbit towards the angle, but you would also think that by tuning the coupling between these layers, you would also tune the spin orbit coupling.
So you want to apply pressure?
Pressure. So
sure.
Do you expect that something similar then to happen as a function of pressure?
I think so.
And is it conceivable that the TC would go
further on? Yeah, that would be interesting. Yeah, I don't know. I mean, 1.5, 2 MeV is the maximum that you could get out of it in the just twisting. But indeed, if you apply pressure, induced spin orbit coupling has to go up. And I'm not aware of anybody trying that.
What do you expect would be theoretically, what would be the limit in TC? I mean, is there some obvious limit or?
Not necessarily because, right. So we expect, according if you believe this fluctuating collective mode story, the best place to be is at the transition, where spin orbit coupling is just high enough to cancel out Bose coupling. So it's a critical story. So basically, you have a disconnected phase, and you want to just destroy it at the critical point is where you have most effective pairing. So if I increase spin orbit coupling, I will just renormalize how much Hertz coupling you need to put in to get the phase transition. Because it will move around in phase space, but I'm not sure whether TC will go up or down. It's hard to know. Yeah. It's a good question. Yeah, but people should try that under pressure. You can also change the TMD. People are studying WS2 and so on. So lots of options.
So in the slide that where you talked about this, like the magnon mediated superconductivity. Like, are you thinking about like? So my question is like, are you thinking about somehow you are exciting some magnons, or like is it spontaneously driven, or like what's the reason? Like the
the magnons are there. I'm not imagining that I'm kind of exciting them with an external drive or something.
But like those will be very low energy.
And that's a good thing. It's like phonons, right? The phonon mediated superconductivity is actually very closely related to this, except that this is internet. But you want the phonon energy to be much smaller than Fermi energy, because that gives you retardation, right? So So you want
like the TC would be like. That's why the TC is so small, like is this.
Right, but so even though it's much smaller than the Fermi energy, the energy of these magnons is not that small. So the ratio of TC over the Fermi energy is minuscule to begin with. So the magnon energy is actually of the right order to explain the TC that is observed experimentally. I think these are indeed low TC materials, a few hundred million. But I think if the you need to have a separation of energy scales between the backgrounds and the Fermi energy. Yeah. Otherwise, there's no reason why you should get superconductivity.
But like, we can also get superconductivity this like this pair in BCS pairing.
But BCS pairing, if you think about it in the frequency dependent way, it also relies on the phonon energy to be much smaller than. Yeah, exactly.
So like, if you compare the energy between the phonon and the magnon, are they comparable or like?
I don't know actually what the phonon spectrum is. But phonons should not care that much on the precise nature of the electronic order. And so yes, that's the idea. If it was really phonon driven, then why would it appear just when this particular type of symmetry breaking appears or not? That seems to be ubiquitous phenomenon in all of these multi-layers. The superconductors always appear very close to some symmetry breaking instability. And so why would phonons, nucleate superconductivity only there? That's why people don't believe it's mostly.
And do you need some finite magnetic field to stabilize the superconductor? No.
I have maybe a clarifying question on the, I think, last or second to last slide when you have these two competing channels. You have this diagram or this figure. This one. What are the curves on the left side of the panel, and the one that's like spiking at one?
Yes. So, and I should say this is a clean limit calculation at essentially zero temperature, right? So it's very spiky. It's somewhat artificial, but this is kind of drew the light peak. This is the condensate contribution. This is quasi-particle contribution, so it's not collective modes, it's excitations across the superconducting gap. And the new thing is within the gap at some finite frequency, this is not a kind of fermionic contribution, it's excitation of this collective mode where the superconducting order parameter starts to do this. That's the resonance rate.
Just another follow-up question. Does the Drew weight and the flapping mode, do they scale equally? In other words, as you introduce the higher temperature, or?
That's a good question. We haven't really done temperature dependent. Seriously.
Just like if you want to one level together, that's the really good problem.
That's a good question. Yeah, we should look into that more here.
So a couple of more experimental questions. How large are these samples?
So that's the problem, right? So then maybe 10 microns or so.
Small. Great. So I guess for that, has anyone done like an RFS experiment on?
In twisted bilayer graphene, there was, I think, one nano RFS kind of experiment. But not on Rhombohedral. Another experimental problem is STM is not possible because all of these interesting phases that have quite high displacement field. You need dual gated geometry.
So I didn't see many pictures, or when you did show them, they went by too fast. So, would you mind talking a little bit about the construction of the? Because you have a lot of gates, you have a lot of things to apply. What does that look like in practice?
That's a good question. So what people do, from my understanding, they put a bilayer and whatever next to that. They want to encapsulate it in HBN, and then there's a graphite gate. That's as much as I know. It's hard.
I think they're 10 micron squares, and then they're bigger of spanning entire scale, at least what I saw.
But then I think the question was then you put HBN and then you put the graphite gates. So you don't have access to the surface. So that would be a problem for ARPAs. Twisted systems is actually a little bit different because the interesting physics happens at very low displacement field, so you can just have it uncovered and you'll see.
I've seen plenty of ARPAs from twisted.
So there's lots of great STM work as well, but neither has been done here. So we're looking at other options.
I just had a quick question. So you mentioned this, the superconducting the superconductivity has to be symmetric, but is there any indication as to what the symmetry?
Yeah, so that's not, I mean, it's very constrained, so I can say that. If you believe there's a single valley and a single spin, it has to be odd parity, it has to be triplet. It cannot be a sway, that's ruled out by definition. So the two options you're left are either noble or chiral. It could be noble P wave or chiral P wave or F, all of the odd parity channels. And generically, almost all calculations find chiral. There's some exceptions, but the reason is just that, if you have a choice between putting a gap, having a full gap, or low energy quasi-particles, if at all possible, you would like to have a full gap because that increases condensation energy. People tend to find chiral. Yeah, but we don't have direct evidence for that. You'd like to do tunneling or something to check whether it's gapped or not, but even that we can't do because of that. Right. So what people do, I think maybe the most promising way to check that, and people in Moiré systems, like Philip Kim has a beautiful paper on measuring superfluid stiffness, exactly using this kinds of microwave experiments. It's microwave reflectometry from this resonator. They measure superfluid stiffness as a function of temperature. And then you can look at temperature dependence. If it's novel, there's some power law you expect. If it's gapped, it should drop exponentially, right? So and in Moiré systems, it's actually nodal. So yeah, they found the power law. So hopefully we can do the same kind of experiments here. Yeah, that would be one way to check whether it's gapped.
Okay, thank you, Ken.